Hello, welcome to our lab report number 2 on electrostatics. Our lab members are going to consist of Alberto Chavez, Daniel Menchaca, Cynthia Ramos Robes, Gerardo Rodriguez, and Christian Reyes. Introduction. Electrostatics is the branch of physics that studies electric charges at rest and their interactions with other charges and materials. In this lab, we'll explore three fundamental mechanisms of charging objects: friction, conduction, and induction, as well as the phenomenon of polarization. By using various rods, cloths, an electrometer, aluminum foil, and a pith ball, we investigate how objects acquire charge and how neutral conductors respond to nearby charges. When two different materials are rubbed together, electrons are transferred from one to another, creating a net positive or negative charge. This is known as charging by friction. By using an electrometer, we can determine the sign of the charge on different rods and after rubbing them with specific cloths, providing reference for controlled charging throughout the lab. Charging by conduction occurs when a charged object physically touches a neutral conductor, allowing electrons to flow until both objects share the same type of charge. In contrast, charging by induction uses rearrangements of charges within a conductor in the presence of a nearby charge, polarization basically, along with grounding to induce a permanent charge on the object without direct contact. Polarization itself is temporary and involves a shifting of electrons within a neutral conductor toward or away from a nearby charge, resulting in attractive forces when through the conductor remains overall neutral. Objective. The lab focuses on observing how neutral, conductive, and either grounded or isolated objects respond to charged rods in different scenarios. Throughout Part A and E, we will determine the sign charges produced by different materials using an electrometer, predict and observe the interactions between a charged rod and a grounded aluminum foil without contact and after contact. Predict and observe the interaction between a charged rod and an isolated pith ball without contact and after contact. Design and perform a procedure to charge a metal sphere positively by induction, demonstrating the principles of polarization and grounding in practice by systematically predicting, observing, and analyzing these interactions. This experiment references the conceptual understanding of electrostatic charging process and their practical applications in controlling charge behaviors in conductors. Materials needed. We're going to be using an acrylic rod, glass, and a PVC rod. We have an electrometer surrounded by a foil cage that's going to help us measure whether the charge of the rod. We have a fur cloth, a silk, and a wool cloth as well to create different types of charges and see how these specific cloths charge these materials. We're going to be using two conducting spheres as well to help with the polarization or curating polarization, and then we're going to be using two conducting rods as well to help us be able to measure whether if to test whether the machine is working properly or not.
So for part A of this experiment, we have to get a charged rod and put it close to the aluminum foil that we hanged on the edge of the table and see what the result of that happened. So in the video, you can see that I grabbed the acrylic and I'm charging it or rubbing against or using a piece of wool to rub against it, and it would charge. The reason we chose this one for part A was because the acrylic with the wool was one that charged the most, I guess, because it had a um, negative 17 electron charge on it. So we thought we'd have the best results with it to like visually see this. And our prediction was that it should attract since it has a really high charge like that. So we should see the aluminum foil really attractive, but what actually happened is that it had very little attraction for some reason. Not sure if I didn't charge it correctly or something, but the aluminum foil just seemed to be attracted to the rod, but it didn't really jump towards it or stick to it or anything like that.
For part B, our prediction was that the foil and the rod would repel each other, and we thought that once a rod made contact with the aluminum, the foil would take on the same type of charge as the rod, since like the same type of charges repel. We expected the foil to move away the second time we brought them close to each other. To carry out the test, we first charged the rod by rubbing it with a cloth, and then we used the electrometer to verify the sign of the charge, and after that we touched the rod directly to the aluminum foil, and this step should have actually allowed some of the charge to transfer by conduction. And once the rod and foil were separated, we carefully brought the rod back toward the foil to see what would happen. And our actual observation of this experiment was not what we expected at all. Instead of being repelled, the foil showed like no clear reaction, and it appeared to stay neutral. And this outcome was very different from our predictions, so it actually led us to think about reasons why this could have happened.
Part C. For this part of the experiment, we had a charged acrylic rod along with a neutral, conductive, and isolated little sphere, or a pith ball. We were tasked with bringing the charged acrylic rod as close as possible to the pith ball without touching the two together and observing the interaction between the two objects. There were two possible outcomes. 1, the pith ball would be repelled, or 2, the pith ball would be attracted. Our prediction was that since the pith ball was neutral, and given how neutral objects are attracted to whatever charge comes near them, be it positive or negative charge, the pith ball would therefore be attracted to the acrylic rod. This was in fact the case, based off of our recordings. Part D. For this part, we once again had a charged acrylic rod, as this was the rod of which we found capable of holding the most charge. The neutral and conductive pith ball was also to be used again. The task this time, as compared to Part C, was to actually touch the rod and pith ball together, separate them, and then bring them back together and observe the second interaction between the two objects. Again, there were two possible outcomes. Either 1, the pith ball would be repelled, or 2, the pith ball would be attracted. Our prediction was that since the pith ball was neutral and conductive, it would absorb the negative charge of the rod and therefore make the rod neutral again and the pith ball negative. Thus, both objects would be attracted yet again, and since it was a neutral and negative charge interaction. Based off of our recordings, we were correct.
Now, for this last portion of our lab with part E, we'll be talking about the concept of polarization. So as shown above, we're going to be negatively charging our rod, and in turn, that'll be rubbing and connecting close to the first metal sphere. That'll in turn attract all the positive charges in that sphere, while all the negative charges are sensed and repelled to the other side of the sphere. And with that, on the other side of the sphere, the positive charge will be attracted to the negative charge that's being repelled on different sides of the sphere. And in turn, that negative charges on the second sphere will be pushed and repelled all the way to the end. So the point of this purpose is to check if we can get positive charges out of that by the concept of polarization and the induction when separating the two metal spheres. So as shown in the video, although we negatively charged the black rod with it, we have a separate rod with the circle attached to it in order to take out positive charges from it. That'll be then checked through our equipment in the beginning throughout the entire lab. That'll tell if something is positively charged or negatively charged. So then by the end, we were able to deduce and find that we were able to grab some positive charges off the process of polarization.
From observing the different charges from the materials, we started with acrylic charged with fur. From that observation, we were able to measure -2 electrons, which means that it's electrically negatively charged. Then when we tried it with the silk, it was the same result as well. We had a -2.0 electron charge making it negatively charged. And then with the wool, it actually shot up tremendously to -17. It was probably it was one of the most electrically charged object we had. Moving on to the glass, it was actually pretty um, not super noticeable, but we were able to get a negatively charged electron. With the fur, with the silk, we were able to get a positive electron from that. It was just one though, and from the wool, it was, of course, it showed more negatively charged as a at -2. So this one with the silk was, I mean, this one with the glass was didn't really show like too much change among the rubbing of the rods. But moving on to PVC, we can see that we actually had a net positive 8 electrons with the fur, with the showing that this was like the most positively charged object we had. With the silk, it was just -1 electron basically. It didn't show too much of a positive charge, so it was just definitely it resulted negative with the silk. But with the wool, we saw actually a net positive of 2 electrons positively charged. So this one with the PVC showed that with these materials, we definitely see a more positively charged rather than negative than the glass and the acrylic.
In conclusion, for part A, we didn't really see too much of an effect happen with the acrylic rod and the foil. There was some slight attraction to it, um, but overall, it wasn't really something that we saw that was really noticeable. But we were able to get some sort of attraction with it. After conducting the foil and the acrylic rod, we thought that there would be a repulsion since both items would be electrically negatively charged. But unfortunately, there was still an attraction happening with the foil and the rod. And we tried multiple times to see if we can get the repulsion effect, but unfortunately, that was not the result. And our prediction was incorrect that there would be a attraction. In part C, we saw that the ball was indeed attracted to the acrylic rod, and our prediction was correct. Since the ball was neutral and the acrylic rod was negatively charged, there should have been a attraction with each other, and the conclusions show that yes, that the ball was indeed attracted to the acrylic rod. Now, in part D, we predicted that there would be a repulsion since both items should be holding the same charge. But unfortunately, our prediction was off again. The balls still seemed to be attracted to the acrylic rod, and we didn't understand why. We tried multiple times to see if we can get the different results, but unfortunately, it was either that there was an attraction and nor no attraction at all.
In part E, we successfully demonstrated charging by induction using polarization and grounding. With two metal spheres, we began by bringing a positive charge acrylic rod close to the two spheres while they were in contact with each other. The presence positively charged rod caused electrons within the two spheres to redistribute. Electrons were attracted towards the sphere close to the rod, leaving the far sphere with an overall deficiency of electrons positively charged. This created a clear polarization between the two spheres. While maintaining the rod near the spheres, we then separated the spheres, effectively locking the charge imbalance created by polarization. After separation, one sphere was expected to be positively charged, while the other retained excessive of electrons, negatively charged. To confirm this, we used a rod to collect charge from the sphere that had been separated, the one closest to the acrylic rod. When measured with the electrometer, this registered a positive tube charge, confirming the sphere had been positively charged by induction. Electrostatic charging and interactions between charged and neutral objects through systematic observation and prediction. By running various rods with different materials and measuring their charge with electrometer, we established a clear reference for the sign and relative magnitude of charges produced by friction. Acrylic rods consistently gain negative charge. Glass rods exhibit both negative and positive charge depending on the cloth used, and PVC rods show strong positive charging with fur and wool. These results are consistent with the expected behavior of materials in the triboelectric series.